Hello. So today we're going to go through slides starting at 24 and talk about how the atomic mass is calculated. So we did do this last year in regular chem, but hopefully you'll remember a little bit of it when we go through it. So the isotopes, remember, are different versions of the same atom. So for example, we have carbon. It's always going to have the atomic number 6. So it's always going to have the 6 protons. But there are different versions of carbon or different isotopes that have different mass numbers. So there's carbon 12, carbon 13, and carbon 14. So because they have a different mass number, they have a different number of neutrons. Okay? So this is the mass number, that's the whole number, protons plus neutrons. The actual mass, because there are some electrons that are in there, even though most all of the mass is the protons and neutrons, the actual mass is these long decimal answers. Last year we used just the whole numbers when we did these calculations. Now for ACE you have to use the actual mass, which is going to be these long decimals. So the isotopes exist in different percentages. So for example, if we look at this one, the percent composition is 98.940 of carbon 12. So that means that of all the carbon that exists, there's these 3 isotopes, but 99%, almost all of it, is carbon 12. So that's why if you look on your reference table at the mass of carbon, it's 12.0107. It's very, very close to carbon 12 because it's mostly all carbon 12. It's a little bit higher than 12.0107, because there is a little bit of carbon 13 and a really, really, really tiny amount of carbon 14. Okay, so this atomic mass is the weighted average of all of the different isotopes. And by weighted, we mean if it's mostly going to be carbon 12, then that's going to be what it's closest to. So last year we used the example that if you took tests and you had, let's say you had 4 90s and then you had 180, you would expect that your average would be closer to 90 because there was 4 of them. You wouldn't want me to just go 90 plus 80 and tell you that your average was an 85. You would want 4 times of the 90s and then an 80. Because you had mostly all 90s. You'd expect your grade to be closer to 90 than to 80. So that's what we're talking about when we say a weighted average of all of the isotopes. So in other words, we're going to count the 12 98 times out of 100, whereas this one we're only going to count 1 time, and this one, basically is negligible. Okay, so that's going to come into account when we do our calculations. So we're going to figure out how this gets calculated using the percents and using the mass. All right, so this is just a mass spectrometer is the way that we determine isotope mass. We didn't talk about this at all in Regents Chem, but here is the sample that we vaporize. The ions and the sample is traveled through this mass spectrometer. There's different magnets that bend it in different ways, and then the different peaks are going to identify what is in there. So this is a way to identify an unknown sample. So this is a lot of times used in like CSI things, or if you have an unknown sample or an unknown product, you'll run it through a mass spec to see what the machine tells you is present. So in this case, you can tell that there is much more zirconium-90 than there is any of the other isotopes of zirconium. All right, so now we're going to work through example number 1. Okay, so I'm going to write the information on this piece of paper, and then I'm going to show you how to calculate it. So we have 75.76% of chlorine 35, and we have 24.24% of chlorine 37. So the chlorine 35 is more abundant, so we would expect that the mass, the atomic mass, the weighted average, is going to be closer to 35 than it is to 37. And if you look up chlorine on the reference table, you'll find that the mass is much closer to 35 than it is to 37. Okay. All right, but last year we would have used these whole numbers. In ACE, we have to use these decimals, and then we'll use these 4 significant figures in the percent to be able to know what to round to, since these are going to be huge numbers. Okay. All right, so we're going to weight the average of the isotopes when we figure out the calculation. Okay. All right, so I'm 75% of this. So it's like, we're going to just say, okay, imagine that there's 100 of them. 75.76 are going to be this. So I'm going to take 75.76, which is the percent, and I'm going to times it by this mass, 34.96885. Okay. So instead of using this 35 like we would have done last year, we have to use the actual. So I'm going to get an answer for that. Then I'm also, for the chlorine 37, I'm going to do 24.24% times this actual mass, which is 36.96590. Okay. And these numbers I just got from your slides. They'd have to be given to you. So that's where I got that information from. Okay. All right. So if I multiply the first ones there, I get 2,649.240076. And when I do 24.24 times that, I get 896.053416. Okay. So just like if I had these grades, I would do 4 times 90, because there'd be 4 of them. We're saying the percent is like base out of 100. I'd get a number, 360. And I would do 1 times the 80, and I would get 80. Then I would add those 2 numbers together. So we're going to add our 2 numbers together. And then in this case, I would divide by 5, because there's 5 scores. We're going to divide by 100 because we're just saying the percents are like as if I had 100 molecules of them, or 100 atoms of them. Okay, so I'm going to add these 2 numbers together, and I'm going to get 3,545.2939492. And then my last step, I'm going to divide by 100. So I get 35, and like I said, we can have 4 significant figures because our percents were only in 4. So 35.45, and our unit will be AMUs, atomic mass units. And if you look up chlorine on your reference table, again, depending on all the rounding that happened, your answer though should be very close to what's on the reference table. And I think it says 35.5 on your reference table, the Regents one. Okay, so you take the percent times the mass, the percent times the mass, you add those values together, and then you divide by 100 because it's as if there were 100 of each one. 75 of this one, or 76 of this one, 24 of that one. And we can see that it's closer to 35 because there was much more of the 35. Okay. All right, and then the next slide, example 2. So now we have bromine. So I'm going to go ahead and use all that information and do the calculations back again on my piece of paper. Okay. All right, so we've got bromine 79, and that's 50.69%. And we're going to times that by the actual mass. So if you look up on your slide, it's 78.918338. And then we've got bromine 81. So this one also just has 2 isotopes. It doesn't have 3 like the last one. And our percent is 49.31%. And then we're going to times that by 80.916291. So you can see that this one is just about 50-50. So we're going to expect that our mass will probably come out to be halfway between those. It's about half 79 and it's about half 81. So it's not so weighted or skewed as the other one was. Okay. All right, so we're going to multiply these two. And we get 4,000.3705532. Then we're going to multiply the bottom two, and we get 3989.98230921. You guys can stop it anywhere along the way. I just can't stop it or it'll take too long to upload. All right, then I'm going to add those two numbers together like I did before, and I get 7,990.35286,243. And then last step, we divide by 100. And again, we can have 4 significant figures because this one's also given in 4. So my answer would be 79.90 AMUs, which, if we're 50% of this, 50% of this, we'd expect it to be 80, halfway between. There's a tiny bit more of 79, so it makes sense that it's 79.9. And if you look up bromine on the reference table, it should be that same thing. Okay. All right, so that's it. And then I'll go ahead and post this and post the questions that you can do in your packet. So hopefully you guys are staying up on those and not falling behind on any of those questions.